fine?
Video is, I don't know, it's slightly blurred.
Okay, I'll just check it out, ma'am.
Okay.
No, Dr. Monica, it's very clear.
Okay.
Yeah,
Okay.
yeah, it's very clear.
Now it's clear. Now it's clear.
ठीक है, ma'am. Okay.
Okay. Pankaj sir, is it okay to start if everything is ready?
Yes, madam, we are live now. We can.
Okay, so you're ready with everything. So we'll ask Garima, you can. Director sir, is it okay to start now?
Yes, please. Please go ahead. Good luck.
So, okay, we'll start. Garima, you can go ahead with your program.
Okay, thank you, ma'am. Since the beginning of time, all living creatures have been and are still being exposed to radiation. Most people are still not aware of the natural and man-made sources of radiation in our environment. Of the man-made sources, the most commonly used is a diagnostic X-ray machine, which is used by doctors to know the extent of disease. The space occupied by these conventional man-made machines was enormous. Some may even be in few kilometers. Over the last 2 decades, the scientists are more worried about the next generation compact radiation sources. These radiation sources have small sizes as compared to the conventional sources. These are also known as tabletop sources. They have potential applications in various areas such as cancer therapy, material studies, biological studies, chemical sciences, etc. Good afternoon, ladies and gentlemen. I extend the warmth of the day to the dais in eminence. I, Dr. Garima Garg, Department of Applied Science and Humanities, welcome you all for the International Webinar Talk Series on Compact Radiation Sources and Application in Sciences, jointly organized by Department of Applied Sciences and Humanities, RKGIT, and RKGIT Pharmacy. या देवी सर्वभूतेषु शक्ति रूपेण संस्थिता नमस्तस्ये 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 नमो नमः. Let's join our hands and invoke the blessings of Goddess Saraswati. May the Goddess of Knowledge shower her blessings in abundance on each one of us. I would request technical team to please play Saraswati Vandana. Technical team, Pankaj sir. Thank you, Pankaj sir. Now I would request Dr. Kumar, HOD Applied Science and Humanities and convener of the webinar series, to please come up and introduce us to the series. Please, ma'am.
Dr. Garima, am I audible? Respected speaker of the day, Professor Zulfikar Najmudin, Department of Physics, Imperial College, London. Dr. Lakshman Prasad, Director R&D, RKG Group of Institutions. Dr. B.R. Somashekar, Director RKGIT. Professor Monica Sasdev, Principal Pharmacy. and also the convener of the series, HODs, faculty members, students, and all other dignitaries and participants present here. I welcome you all for this 3-day webinar series on the compact radiation sources and applications in sciences, organized by Department of Applied Science and Humanities, RKGIT, in association with RKGIT Pharmacy. RKGIT was established in year 2000 and being rated as one of the best multidisciplinary institutes in Delhi NCR region. The institute provides technical education in B.Tech, M.Tech, B.Pharm, M.Pharm, MBA. In B.Tech, we have CS, ME, Civil, IT, Electrical, and Electronics Engineering branches. From this year, we have introduced 3 upcoming branches of computer science, namely Internet of Things, Artificial Intelligence, and Machine Learning and Data Science. Applied Science Department is pursuing research in high-power laser plasma interactions. RKGIT Pharmacy is accredited by MBA and was ranked 29th in NIRF 2016. The institute is also an approved research center for PhD by AKTU, Lucknow, and research related to nanomedicines is being carried out in the Pharmacy College. Now about the webinar series. The webinar will focus on compact radiation sources and application in sciences, example medical sciences, biological sciences. Scientists have used radiations for more than a century to elucidate matter's microscopic nature. The enormous impact factor of X-ray science has led to more than 24 Nobel Prizes in physics, chemistry, and physiology and medicines. Over the last 2 decades, the global aim of scientists is to undertake the novel challenges of developing the next generation compact coherent radiation sources, which have the potential to make them widely available and relatively inexpensive, and thus enabling many applications such as cancer therapy, material studies, chemical sciences, etc. The laser can produce 0.1 to 1 femtosecond electron bunches from plasma, which gives the possibility of an ultra-compact, ultra-bright, tunable X-ray and gamma ray sources. For the present webinar series, we have 3 speakers who will be enhancing our knowledge in compact radiation sources and the application in the various fields. The first speaker, that is today's speaker, he'll be addressing today is Professor Zulfikar Najmudin, Faculty of Natural Sciences, Department of Physics, Imperial College of London. He will be speaking on radiation sources from laser accelerators and applications. The second speaker for tomorrow is Dr. Antoine Maitrallain, Research Fellow, Department of Physics, University of Strathclyde, Glasgow, Scotland, UK. His topic of webinar will be laser-driven sources in radiotherapy. The third speaker of the series will be Dr. Jonah Renshaw, Associate Professor, Department of Civil and Environmental Engineering, University of Strathclyde, Glasgow, Scotland. And she will address on 16th September on the topic, the use of synchrotron radiation in applied geoscience. So that was all about the webinar series. And now I hand over to Dr. Garima. Over to you, Dr. Garima, over to you.
Thank you, ma'am. Thank you for introducing us to the series. Now, I would request Dr. D.R. Somashekar, Director RKGIT, to please welcome the gathering. Please, sir.
Thank you, Dr. Garima. Good afternoon, ladies and gentlemen. Honorable Speaker of the Day, Professor Zulfikar Najmudin, Faculty of Natural Sciences, Department of Physics, Imperial College of London, UK, and Deputy Director, the John Adams Institute of Accelerator Science, Imperial College London, UK, respected Director R&D, Dr. Lakshman Prasad, the conveners of the International Webinar Series, Professor Dr. Monica Sachideva and Professor Poonam C. Kumar, Professor Monica Sachideva, Principal of the RKGIT Pharmacy, and Dr. Poonam C. Kumar, HOD of Applied Science, RKGIT. Co-ordinators, Professor Dr. Sanjeev Goel and Abhinav Agarwal, Dean Academics from RKGIT Pharmacy. Co-coordinators, Dr. Vikas Katoch, Associate Professor, Applied Science Department, RKGIT. Mr. Pankaj Kumar Sharma, Assistant Professor, RKGIT Pharmacy. Committed band of teachers, and more than all, the participants from the different institutions affiliated to the AKTU and other affiliated institutions and universities, and my dear friends. At the outset, let me congratulate the Department of Applied Science of RKGIT in collaboration with the RKGIT Pharmacy to bring out this international webinar series of 3 days from today till 16 September on a new topic, the compact radiation sources and applications in sciences.
जो जेई मेंस है
Friends,
इसमें एडमिट कार्ड आया है, मतलब एक रिजल्ट आया है वो
Dr. Garima, kindly mute that gentleman. Yeah.
Sir, I have done.
Yeah, thank you very much. Right. Friends, if we today talk about the advancement of the technology or advancement of the science, what actually the science is? Friends, to tell you in a simple way, science is a way of helping the brain to grow in finding new knowledge. And what actually, say today, what is that we have been seeing? The corona effect and its turbulence and what is its effect on the economy. See, through this science and the applications of this science, we can bring out in a satisfactory way of basic human needs and improve living standards. Friends, if you talk about the new educational policy, so even the new educational policy, it is focusing or emphasizing on the research and the innovative projects. So I am very happy this international webinar is in line with the national education policy for our own self-sustenance. So this is also one of the important factors of the national education policy. Friends, if you talk about the transmission of the electricity, today, the New Zealand is the first country which is transmitting the power without any wireless. Then you can think of what is the radiation there. Say, what is the effect of radiation on the human body or human beings or the creatures, so on and so forth. Say, these are all the challenges. So in the coming new era, and particularly the once again, I compliment the COVID-19 because so this has given a solution, a nature solution to one and all. So whether it may be in a corona or tomorrow it may be in a corona something, or even today the cancer which is suffering the human beings, say it is the out of science, my dear friends. So friends, so science, if this science does not exist, let me tell you, there's no universe. So all will be zero. So friends, so kindly make use of this, the international webinar series, so particularly on the latest subject, and hope to mera itna hi submission hai to all the conveners, the coordinators, co-coordinators to bring out a research paper, and not only just in a paper, so bring out from the research projects in the campus and in their respective institutions. So friends, I don't want to be in between the honorable speaker who is a great scientist and the scholar. So they are all big science people. So I don't want to be in a small way. So I don't want to be in between you. And I wish all the success of this 3 days international webinar series. Thank you very much. Jai Hind, Jai Bharat Mata. Over to you, Garima.
Thank you, sir. Thank you for your welcome address. It is our privilege that amongst us today we have Professor Zulfikar Najmudin, Imperial College London, UK. Sir, it is our honor and privilege to have you with us today. I, on behalf of RKG Parivar, welcome you for this session. I would request Dr. Monica Sachdeva, Principal, RKGIT Pharmacy and convener of the webinar series, to kindly come up and introduce our speaker to everyone. Please, ma'am.
Thank you, Dr. Garima. It's my privilege to introduce our eminent speaker of the day, Professor Zulfikar Najmudin. Sir is currently working as Professor of Physics at Department of Physics, Imperial College of Science, Technology and Medicine, and Deputy Director of the John Adams Institute for Accelerator Science, Imperial College, London, UK. Professor Zulfikar Najmudin received his BA Honours and MA Honours degrees from University of Oxford and PhD degree from Imperial College, London. He has directed the work on Wakefield acceleration at Imperial College since he joined the group as a PhD student in 1991 under the supervision of Dr. Bakar Dengar. He was directly responsible for the first measurements of electron acceleration with energy greater than 100 microvolts and the first measurements and simulation of a narrow energy spread, and also the suggestion to perform phase contrast imaging with the betatron radiation from laser Wakefield acceleration. He has also made significant contributions to ion acceleration with lasers as well as the general study of fundamental laser plasma interaction with at high intensity. He has published more than 250 research papers in reputed journals like Nature, Nature Physics, Nature Communications, Science, etc., and has garnered over more than 14,272 citations and a H index of 60. A recent highlight is the demonstration of the brightest narrow energy spread proton beams yet produced in a laser-driven interaction through novel laser gas jet interaction. He developed the X-ray phase contrast imaging with compact plasma-based accelerator. He has taken the first step to make the much easier and cheaper source which produces very high energy, high quality X-rays to examine everything from molecular structure to the integrity of aircraft wings. Sir has supervised 25 PhD students and has a strong record of obtaining various fundings for and grants, having been an investigator and a co-PI. Since last 6 years, he has also got big grants for the AWAKE, that is the Advanced Proton-Driven Plasma Wakefield Acceleration Experiment at CERN, design study for plasma-based free electron laser, Sir is also a fellow of American Physical Society and Institute of Physics. With these great words, sir, I welcome you to our institute to have and want to listen from you, sir. Thank you so much, sir. Thank you. I invite you, sir, for your talk.
Okay, thank you. Thank you for the introduction. And welcome from London. Just show my slides. You can see that? Yeah?
No, sir.
Oh, wrong one, sorry.
Yes,
about
we
now?
can see now. We can see.
You can see?
Sir, it's visible.
We
Yes,
can
sir.
see, sir. It's visible.
It's gone to the wrong screen, though. It's a bit strange. Hang on.
It's perfect, sir, now.
Yes, sir.
You can see?
Yeah, we can see your screen.
Yeah, I think it's the wrong screen, though. Hang on. Sorry. You can see this. Can you see my pointer?
So right now we can't see. We can see you.
And you can see this
Right
pointer?
now, no, we can't see the screen now. Initially we could see. Initially we could see your screen. Right now we can't see your screen.
Okay, sorry about this. Let's try this again, you can see a screen, right?
No, sir. No.
No, sir, your screen is not visible.
I need to keep pressing this button, sorry. How about now?
Yes, sir, your screen is visible, but not the slides. Your desktop is visible.
Yes, now,
it's visible.
All right, okay. Sorry about that. I don't know, Zoom seems to have a mind of its own. Okay, so start again. Thank you again for the invitation to speak to you. Thank you, Pawan Kumar, especially for the invitation. As you heard in the introduction, I'm going to be talking about radiation sources, particularly the work we're doing on compact X-ray sources. And so before I do that, maybe just a little introduction. I think you heard some of this already, and many of you will know this. But the discovery of the X-ray, the invention of the X-ray machine, things that can take X-rays, has made a huge difference to all of our lives. I'm sure all of us have been to a hospital and had an X-ray taken, right, one time or other in our lives. And that came directly from a physics discovery from William Röntgen, just before the turn of the 20th century. He discovered that when you struck electrons from a X-ray, from a cathode ray tube to a target, it produced radiation was penetrating. And that was the most important thing that he discovered about X-rays, right? The most exciting thing is that it was able to penetrate through matter and be able to see inside of it. So for example, one of the very first things he did, as I'm sure every scientist would think of doing, is if there's a radiation source, you get your wife and you tell her to stand in the radiation source. He did not get her to stand in it. There's a picture of her hand, which is very famous. There's a picture of his wife's hand. And of course, Röntgen was awarded the first Nobel Prize, the 1901 Nobel Prize for this discovery, which has pretty much changed all of science. So it's a worthy first Nobel Prize. That kind of X-ray machine, I mean, if you do go to a hospital and an X-ray taken, that is pretty much the type of X-ray machine that you will be using. It's something called a first generation machine. The X-rays are generated when electrons hit the target and are decelerated very fast, right? Radiation is produced when charged particles such as electrons are accelerated or decelerated. And so that's what's happening within that target. The electrons are stopped almost instantaneously, and the momentum has to be conserved, given off as X-rays. And we can use those X-rays. And as I say, those X-ray machines are used in labs all around the world, plentiful, and they're used in hospitals and things, of course, for doing X-rays as well. One thing you can notice about those sources, though, is that the resolution is kind of limited. Because it's an electron that's going into a target, there's some limit to the size of the radiation source, which limits the resolution. And also there's a limit to the amount of energy, the amount of photons you can produce. If you just try to put more and more electrons into the target to produce more and more X-rays, at some point you actually just melt the target. And so these first generation sources, though they're around all over the world, there's a limitation to what they can do. Another discovery, another byproduct of a physics experiment was when people started making particle accelerators. So particle accelerators, again, you probably know, people smash particles together to create different new forms of matter, and we learn about the universe by doing that. And again, in early physics, there were many particle accelerators. One particular type of accelerator is one that makes particles go around in circles, so that you can accelerate them slowly, but still to high energy. When they started to get into reasonably high energy electrons, high energy particles around a GeV of energy, what physicists discovered is that actually whenever an electron went around a corner through a magnet is what keeps it going around in a circle, there would be radiation produced. Again, this radiation produced is to conserve momentum, right? The electron is going off in this direction, so some momentum must go off in this direction. And again, that radiation, at first, they obviously were not happy because it was losing energy from the particle beam. But they soon realized this parasitic radiation could actually be very useful in itself. It would be very bright, and so that they could use it for actually doing things like imaging as well. And so this second generation of particle source became a byproduct of wherever there was a high energy particle physics experiment, they would have parasitic beamlines to be able to use those X-rays and to be able to do, because the electron beams that produce these could be much, much smaller, they could do much higher resolution imaging, they could do more advanced X-ray studies with these devices. And it became such a, it became so important, this application of the particle accelerators, that pretty soon people realized that there was actually more demand for the X-ray radiation than there was for the particle collisions, for the high energy physics experiments. And so actually that led to dedicated facilities being produced to produce X-rays from this, what's called synchrotron radiation, this bending radiation here. And in fact, another thing that they did is, so normally if you go around in a circle, then obviously that radiation is also going around in a circle, all in different places. But what scientists realized is that if they actually made a magnet chicane such that the electrons would go in a circle in one direction, and then the poles of the magnet would change so that they would go in another direction, and so that they would always be curving, but they would roughly be going in a straight line. What you can see is that this synchrotron radiation produced in this kind of device actually all goes in the same direction rather than in lots of directions. And so that can add up and make the source even brighter. And so that's what was called a third generation source when the X-ray from the particle accelerator became more important than the particles themselves. And that led to this third generation of synchrotron light sources. Again, there are a number of those. I'm going to show them in my next slide. This thing in particular that actually makes the radiation go in a line is something called a wiggler. And again, we'll talk about that in some detail later. Recently, people have gone beyond even the third generation source into something that are called free electron lasers, X-ray lasers, that you might have heard about as well. There are a number of X-ray lasers. In fact, what happens is if this length becomes long enough and the radiation given off is in a small enough wavelength range, it can actually feed back on the electron beam and cause a kind of instability loop that actually amplifies that radiation. And that amplification process is a laser. Actually, this is the laser beam. This is not a normal laser beam. This is an X-ray laser beam produced on the SLAC CLS, which is an X-ray laser. There's a few X-ray lasers in the world. There's not many of them, but they are incredible brightnesses of X-rays. I mean, we are talking 20, 30 orders of magnitude, almost greater, something parameter called brightness than the original X-ray sources. So that this evolution has been amazing. And in the meantime, again, I mean, I know you're from all different areas, but probably even in science, you've come across some of these different applications. So not just medical imaging, but you will have come across crystallography, where you discover the structure of things even smaller that you can't directly image. So even smaller than the wavelength of light. So atoms and the atomic structure of proteins and things like that. And through crystallography and of crystals themselves, obviously, magnetic resonance imaging, understanding the structure of magnetic materials, coherent diffraction imaging, which actually is an advance on crystallography. It is actually using the phase properties of free electron lasers to be actually produce holograms, if you like, of very small structures, and things like absorption spectroscopy as well, where you determine what the makeup of the material is as well. So there are many applications. I'm not going to talk about all of them. I'll show you some of them later in the talk. I said that there are a number of the third generation and above synchrotron light sources. You can actually look them up on this website. There's a whole website dedicated to them. And they're all over the world. There's one in India, in RKGIT, in Indore, the Indus facility, which is a third generation synchrotron. But now there are also these fourth generation light sources, the X-ray lasers. Probably the two most famous are, in fact, old particle physics experiments, very famous particle physics experiments. This one is in DAISY, which used to be electron-electron collider, electron-proton collider. This one is in SLAC, which in California. and again, made many discoveries in particle physics. Some of the Nobel Prizes that the structure of the universe is based on happened with this particle accelerator, which was a particle physics experiment. It's now been completely converted into a light source. All it does now, or its main job, is to produce radiation for the applications that I talked about. The thing, though, that you might already notice about these things, and so actually there's no scale on this this diagram, but there is on this, is that you might notice the slack itself is a couple of kilometers long. So these things, to be able to get to 2 GeV and above, which is where I said radiation starts to become important. Some of the FELs, some of the synchrotron sources are now even higher energy, they're 10 GeV and above. For that, you need quite long lengths. And the reason you need long lengths is because of the way that the particles accelerate. They're accelerated in copper tubes through which electric fields are passed at radio frequencies. There's a wave, an electric field wave that passes through these tubes. And again, just like there's a limitation on how much radiation you can put on a first generation light source, there's a limitation of how much of this RF radiation, how big the electric field you can make on these accelerators is. That typically is around 10 to the 7 volts per meter. It's the breakdown voltage. You know, if you made the fields any bigger, it would just destroy the material that actually holds the fields in place. And so the problem, that's a big problem, not just for light sources, it's a big problem for particle physics as well, because people are thinking about the next generation of particle physics experiment, and what they find is that they can't afford it, because to make the next generation of particle physics experiment, you would have to take one of these, like a slack accelerator, make it 10 times longer, and that suddenly becomes more expensive than any government actually wants to spend money on at the moment. But anyway, not talking about particle physics, let's talk just about X-ray sources. Even for these X-ray sources, an FEL is probably out of the reach of India at the moment. It's been on the table in the UK for a number of years. They've been talking about making an FEL in the UK, and they can't afford it. It's a billion pound, $1 billion facility to begin with. So even though the science that they do here is amazing, there's a Nature paper almost every month that comes from LCLS. Being able to sit on a table and have one of these things is only for the privileged few. So okay, so having established that, what we would like to do is to be able to bring particle accelerators of that order to make them more common, to bring them to more widespread use. And so one of the ideas for doing that is to use plasma accelerators. So a plasma, as opposed to like the copper tubes that we talked about, which were the conventional accelerators were housed in, a plasma in this, some of you may have a medical background, has nothing to do with blood. I would not be working in this field if it had anything to do with blood, because I'm definitely queasy when I see blood. But a plasma in this sense is actually a collection of electrons and ions. It's material that's already been broken down, it's already been ionized. And because of that, because it's already been ionized, you can't break a plasma down anymore. In particular, if this is a graph, which there's not too many graphs and not too many equations of this talk, but here's a graph which is going to demonstrate something called the plasma wave. And what it is that there's an initial density of electrons, an initial density of ions. And if I go further, you can see if I can make a wave pass through that medium, this plasma, I can actually separate the electrons from the ions if I do it just right. And I can calculate what the field associated with that separation of electrons and ions. And you come to a very simple formula. This was suggested. Well, it was suggested in Russia, but the real idea of a plasma accelerator was suggested by Tejima and Dawson in a paper in 1979. And this simple formula tells you that if you have a density of plasma, which is, say, around atmospheric density, maybe a 10th of atmospheric density, a 10th of atmospheric density would be about 10 to the 18 particles per centimeter cubed. If I take the square root of that, I get 10 to the 9. This is of order 1. So 10 to the 9 volts per centimeter, I get an electric field, which is 100 gigavolts per meter. 100 gigavolts per meter. Again, if you don't know the energy scales of these things, 100 gigavolts is the energy, roughly it's the mass. If you take all of that energy and turn it into a particle, it's about the mass of a Higgs boson. So if, for example, you wanted to make a particle accelerator that was just studying creating Higgs bosons and generating lots of them, like a Higgs factory, you could do this in a couple of meters. You could have one side which is an electron accelerator, one side which is a positron accelerator, and collide them, and you would produce lots and lots of Higgs. Well, I say lots and lots of Higgs particles. They're pretty rare even when you do that, but enough to have much better statistics, much better understanding of interaction and the way they do it now, which is throwing protons against protons, in which case the production of Higgs is very rare. Obviously, the same way that we could shrink a particle accelerator down to meter scales, we could think about doing the same thing for light sources as well. So that's amazing. If we could make these fields, and an important thing is that obviously, if you just let the field be stationary, then a particle would drop down the potential, the electric field. The potential actually follows the density, so it would fall down this hill. It would gain energy, but then it would lose energy again as it goes back up the hill and down again. And so you wouldn't gain very much energy actually in that way. What you really need is for this whole structure to be moving at the speed of light, so that as a particle accelerates, it moves forward, and then this whole structure moves forward with it. And so that's the idea of an accelerator. That's how the electric fields in a conventional accelerator work as well. And so this was actually what Tajima and Dustin suggested. So what they suggested is that if you have a laser pulse that's intense enough, imagine that you have a laser pulse within a plasma, then it would actually, the force of the laser pulse would, if it's intense enough, you can actually make the laser push plasma electrons away from the ions, because the ions are heavier. They don't react so quickly to the laser, and so you get this kind of structure. You get within the plasma, you get a cavity. And what you might see by the cavity is obviously there's a force on the electrons trying to push them back to the center. Now, because this whole thing is moving at the speed of light, the actual initial plasma electrons, as they're pulled inwards, this whole thing moves forwards. And so actually they return on axis by the time the laser pulse is gone, by the time this cavity is gone. And so when they arrive, there's nothing to stop them anymore, and they overshoot. And you actually get this wave structure formed in the back of the laser pulse, something called a wake field. However, if you add an electron which is traveling very close to the speed of this structure, now as it sort of slips slowly back in the structure, it actually sees that accelerating field, and it can start, if it gains enough energy, it can start and move forward and actually gain energy from that structure in itself. And the energy that it gains, again, another formula that's not important, but it depends on the gamma factor, the phase velocity of this plasma wave. So the faster you can make this thing move, the closer to the speed of light you can make it move, the higher the energy gain can be. Here I'm going to show you some PIC simulations. That was obviously just a cartoon. This is actually numerical simulations that we do of an interaction that we do, experiments that we do. And this parameter here is the laser strength in each of those cases. And so if I show one example here, you can see as the laser pulse passes, then indeed you can see this wave structure, exactly the kind of plasma wave that I talked about. So for a relatively lowish intensity, this is still a pretty high intensity laser. I'm going to go into that in detail, but you can see that that plasma wave can actually be generated, and so that there are accelerating fields associated with that plasma wave, and it's moving at the speed of light along with the laser pulse. If I go to a slightly higher laser intensity, you can see that plasma wave actually becomes stronger. It actually, you can see at some points there's that cavity-like structure that I talked about, and actually becomes decoherent after a while. But along with the laser pulse, there was a nice cavity that went along and could be used for acceleration. Now, if I go to even higher intensity, you'll see that cavity form really clearly. You might also see those things. Did you just see those? Hopefully these animations are moving in real time. Let me do that one again. That's the low intensity wave produced, that's the cavity produced. And you'll see here, you'll see maybe some of these particles actually pushed forward, directly pushed forward. And so that answers another big question is, okay, I've got an accelerating structure, but how do I put particles within that accelerating structure to accelerate them? And actually, it turns out that if you try it hard enough, you can actually pull them directly from the plasma itself, and they can follow the laser pulse, and you can get energetic electron beams directly from the plasma. And in fact, we do this. We do this routinely. So this is done on a laser pulse, which is at the Rutherford Appleton lab. Some of you might know the Rutherford Appleton lab because it has a big synchrotron source there, which is called the Diamond facility. But also on the same site, there's a laser, one of the premier short pulse lasers in the world, the Gemini laser. It produces something like 10 joules of laser energy, which doesn't sound a lot. But when we put it into something which has very small dimensions, like microns in transverse size and tens of femtoseconds in duration, actually the intensity becomes so large that you can actually have these plasma waves produced. And these are actually electron beams that we produce. We disperse them with a magnet, and you can see that how much they disperse depends on energy. You can see some of them go up to about 2 GeV, which is the order of energy that I said, where you start producing copious amounts of radiation. This is just acceleration and deceleration actually showing that we do have, we basically have a GeV in this case gain in less than half. This unit was a half millimeter here. So. Okay, so indeed we can generate these very energetic particles in a very short time duration, and they will produce radiation. Because actually, what I should have said, what if you saw my cartoon from before of the accelerating particle, actually there was something wrong about it. I showed a nice smooth acceleration of the particle just like this. Actually, that's not what happens at all, because when they get to axis, they also have this transverse momentum. Because of the forces on the electrons inwards, actually the electrons will overshoot, even the ones that are accelerated, like I talked about these ones overshooting, even the ones that are accelerated will overshoot, and they will start to do this kind of motion, right? They'll overshoot, get accelerated, and then overshoot again, accelerated, overshoot, accelerated. They very much have like if you remember right at the start of the talk, I talked about the wiggler motion. I talked about how each of these curves produces a little bit of radiation. You can see that we have something like that wiggler motion, and each of these curves will produce radiation, and they'll all be produced in a beam that will go in the forward direction and explained by standard, the same kind of formulas that are used in conventional synchrotrons. And indeed, so we do experiments to look for this radiation. So here's what our experiment looks like conceptually. There's this laser pulse. There's this intense short pulse laser focused tightly into a gas medium. I said all you need is a gas medium, roughly ambient density. And out of the back of this gas cell, simple enough, comes, well, there'll be some laser energy which is unspent. So we get rid of that with a foil. Then you are left, after the foil, you are left with a combination of electrons and X-rays. The electrons here in blue, we pass through a magnet so we can actually look, like I showed you in the previous slide, look at their energies onto a screen. And then all you're left after that is a pure X-ray beam. It's a slightly divergent X-ray beam, so that's good for magnification. You can put a sample somewhere in that X-ray beam, and somewhere later on a detector, you will see an image of that X-ray beam. And this is exactly what we've done here. This is a couple of targets. I'm not sure if you can see the smaller feature one, but it's out in big here. So this one is a wire mesh. There's a couple of wire meshes, the old wire meshes, copper grids. This one has 5 micron structure, and you can see that very, very, very clearly resolved. Make a very clear image of that. And so this, I should have said, this is the image produced by the X-ray radiation that comes directly from that little mini accelerator. The other thing I should have said of this is getting to GeV in some few centimeters rather than those big facilities that you saw before, which were 100 meters, maybe even kilometers inside to get to GeV. So this is it's not a beautiful way. The beams we produce are not amazing. They don't have very narrow energy spread. They can be very, very variable in energy and structure, but they produce very, very short distances, and they produce a lot of X-rays in the same time. So some of the properties of that X-ray beam are actually quite interesting, because because the spatial dimensions are very small, the wavelength of that the oscillation is very short as well. And when that's Lorentz boosted, so all of this, that wiggling motion produces the radiation, and then the fact that it's produced by relativistic particles makes it boosted high energies. That's what makes it X-rays. And in this case, we can get to very, very high photon energies above 25 kilovolts. So that's very good for trying to image dense materials, because the higher energy, the more penetrating those X-rays are. I already said it has a very small source size, which makes it a very high resolution. It also means that it has something called spatial resolution. I'll come back to that in a second. It's a small divergence, so it's a beam, which is good. Unlike the radiation sources, some X-ray sources, like the first generation X-ray sources, actually produce X-rays in all directions. So you have to be very close to be able to get a good dose of X-rays. Also, you can't really have a very high magnification, because if you put your detector very far, then all the X-rays have come off into a big cone. So that small divergence actually is very useful as well for imaging applications. But it has some small divergence, so you can do magnification with it as well. It's a very short pulse, so it's good for making snapshots of things. I'll show you an example of that later. And it's also bright. You could see the image I showed you was done on a single shot. It was more than bright enough on a CCD camera to be able to produce images. So that's important property. Let me talk a little bit more about this spatial resolution. Sorry, I didn't mean spatial resolution here. I meant spatial coherence then. So I said the source exhibits spatial coherence. So just like the impact source, where photons are produced at random times by the electron beam, our photons are also produced at random times. And so you'd think that this is not a coherent source. There's no set time where one photon wiggles compared to another photon wiggles. And so things like interference, diffraction, you think you wouldn't be able to do that. Actually, it turns out that even if you have interference sources, and so if you've done a first course in optics, maybe you know this already, but I'm not sure it's something that everybody knows, is that if you actually have a small source and you let it propagate outwards, actually at a far enough distance, even though initially the radiation produced was incoherent, and if you tried to look at the electric field at any given point, you wouldn't find a spatial relation sorry, between the particle and its phase. Sorry. But if you wait long enough for the particle, I've got some water. I brought some water with me. I've got a water bottle here. Sorry, excuse me for a second. That's better. Okay. So I was talking about even if you have an incoherent source and you wait long enough, if you go far enough away from the source, you can actually make some kind of coherent. You can actually look at the wavefronts, and they look over a small distance. They look relatively uniform. The best example of this I have, if you if you don't understand that, is it's not good. Is if you throw if you've ever been to a pond and you've thrown lots of pebbles into the pond all at the same time, and you will see the waves generated on the pond, which all look kind of incoherent, very close to the source. But if you look far enough away, you'll actually see spherical waves emitting, which look like all of those pebbles were pushed in at the same time. And effectively, that's what's happening here, is that the X-ray source, even though all of these are produced, all these X-rays are produced at random times, if you go far enough away, actually the distance to the detector, to the object, becomes more important than the relative distance between each of those sources. And so actually the phase becomes quite uniform. And you can actually use that for doing interference effects. So if you have something that generates spatial coherence, actually what you'll see is you won't just see the shadow anymore of the image, but you'll actually start to see interference effects. So you'll see places around the edges in particular where the contrast is enhanced. And this thing is called phase contrast imaging. The spatial coherence enhances the image. And so I can give an example. So say I have this object, which if I just looked at that object, just with a detector right at the back of this object, that's what it would look like. And that would be the normal absorption contrast. You can kind of see it's a bit darker here because some of the X-rays have been absorbed in the center. But now if I move my detector far enough away, you can see these X-rays, as well as being absorbed, they are also being deviated slightly. And because of that deviation, there are light and dark patches. And that's what happens when you have phase contrast. You actually have these areas where you see the edges particularly strongly enhanced. Okay, so we wanted to see if our source was any good for phase contrast imaging. And one of the first things you do, one of the easiest things to get phase contrast with is to find an insect lying around. And so actually this is what this is in a few keV, not particularly hard photons, but what an image of a fly would look like in absorption spectroscopy. So this is with a detector placed right behind the fly, so it has no chance for those beams to diverge. And you can see that there are dark and light areas where there is denser material, the absorption is greater, and so it looks darker. However, if you move that detector away from the fly, what you see is the same fly has now so much more information. Actually, you start to see the veins within its wings, you start to see the flesh around its legs, you start to see these hairs. And all of these things have happened because of that process that I told you, that the X-rays are not just being absorbed and transmitted, they are actually being diffracted a little bit as well. So this is an interference effect. That's called phase contrast imaging. And this is actually for our source, because it is such a small source, actually that phase contrast happens much more quickly than with the standard source. And so that's one of the real exciting applications for our source, actually. Makes it a little bit different from other sources even, just that source size is so small. This thing is going to come out big, just so you can see it in more detail. We've applied phase contrast imaging not just to biological samples, we've applied it to materials as well. So so actually I didn't put some of our latest work. Some of our latest work is actually using this radiation source to look at industrial samples. So we've been looking at carbon fibers and breaking carbon fibers that you would not normally see in just standard absorption spectroscopy, but you do see in phase contrast. We've been looking at battery cells, composite materials, and things like that as well. But this one is a particularly nice example because it's a physics example. This is a target that's going to be hit by a laser pulse. And again, what you see, we actually put some corrugations here. What we were trying to do is like make these little jets here, and these little jets produced by something that's an instability. It's a Rickmeyer-Meshkov instability. Not really important what it is. And it's a silicon target. But actually what you can see is that, well, you can see things that you might have expected as like a shock wave that passed through and destroys the material. And these regions of darker density are again because X-rays have been absorbed. So it's a standard absorption spectroscopy. But one thing we hadn't anticipated is, for example, you can actually see a weaker shock. I don't know if you can see this here, 30 nanoseconds. You can actually see this more spherical but weaker shock, which is preheating the target and actually explains this kind of behavior at later times. That thing we can only see, you can see it's the dark and light thing again. It's only observable because of the phase contrast imaging. We would not have been able to see this in standard imaging techniques, but it helped explain exactly what happened to the target at later times. And the other thing I can demonstrate with this example is actually, you can see that the time scale that I've done this over is nanoseconds. So actually, these are all different shots. This is not the same shot. This is all different shots. But what we've done is, because we have a laser pulse, an X-ray source, which is synchronized with our laser pulse, and we can actually change the relative timing on a very small scale, on the nanosecond scale, meter scales, almost few meter scales. and actually change when in the interaction we're looking. So we can actually see these different features as they propagate in time. And because, again, because our X-ray source is so short in duration, it's as long as the electron bunch, which is as long as the laser pulse, which is about 30 femtoseconds or so. All of this imaging, these things are traveling, a thousand of the speed of light, but still they're effectively frozen because they're snapshots within the X-ray image. So that's another really important property of our X-ray source. I've been told that you've seen some of these before, but I put this example again because just to go back to bone, I think bone imaging is the thing everybody compares X-rays to. And again, you probably have had an X-ray, and you kind of know, of your bones in your body, and you know that a standard X-ray will be kind of grainy. You won't be able to see. You won't be able to see much feature. So, for example, you've had an X-ray of your leg taken, maybe, and you will know that you can see the femur quite easily. But this is actually a sample taken from somebody who had osteoporosis, so brittle bones. And a bit was cut out from the bone and actually put into our X-ray imaging. And actually, you can see here much more detail than you would normally see in an X-ray, because our source size is so small and we've magnified, and so you can actually see quite a lot of the detail. Actually, you can see the structure of the bone. The bone is not solid; it's actually very open. This is where your bone marrow is. This is where your blood is produced. So this is plasma being used to study plasma, if you like, or plasma formation, anyway. Actually, we didn't just take one image. We actually took a whole sample of images that we rotated. And maybe you can see that as we rotate some of these structures, you can actually start to see you can imagine what the 3D structure is. And so actually, I don't have time to talk about that, but there is a process, there is a mathematical way of turning this, different projections, looking at different angles, X-rays at different angles of the same sample, and turning them into a 3D image. And you can do it slice at a time, and add the slices together until you get a 3D image. And that process is called topography. So this is the 3D tomograph that we produced in that interaction. The scientist, not one of our team, but the scientist who gave us this bone sample, he's very interested in looking at the structure of this bone sample because he's actually those bone samples came from people who were given a particular drug, which was supposed to make their bones stronger. These were for old age women who were having hormone treatment and as a result had weak bones. They were given this drug to actually try and make their bones stronger. And what it turned out is that actually the drug they were given made the bones stronger but more brittle as well. And so actually within this structure, you can actually see places where there are breakages within the bone structure. And that's what caused them to their hip bone to fracture and why they needed hip replacement surgery. And so being able to study the bones that came out was quite important. Being able to study it in live would be even better. That would be a next step for us. But it's not just bone. Even X-rays, and now people in the synchrotron labs, people are actually thinking about, because of these special properties of phase contrast imaging, people are looking at things which you would not otherwise see in X-rays. So, for example, these are both breast and prostate samples. The left-hand side is done with an X-ray machine, which has phase contrast imaging. The right-hand side is just a standard histology in a microscope where you take off slices, stain it, and then look under the microscope to see that structure. The same for the prostate. Here, the left is the X-ray. This is the histology. You can see that the X-rays actually can be as good a diagnostic, maybe even better in some cases, of the flesh as the standard microscope image would be, and maybe a lot less effort to do as well. So we try to do that again with our X-ray source, and so this is now of prostate sample, and indeed you can actually see the features within that prostate sample. This was kind of a large prostate sample. It was over a centimeter, it says 3 millimeter, but I think each of these frames is 3 millimeters or something like that. And so now we've moved our X-ray image along because it's such high magnification, and we've created you know, a mosaic of that structure, and then we can stitch them together to produce these relatively large images of something that you would not normally see an X-ray image of, right? Just soft tissue. So that phase contrast imaging actually shows phase contrast imaging. Probably its most, I would say, interesting application. Here's another example. This is a breast tissue. On the left, you don't see very much, but after a little bit of manipulation, actually what you see is, if you can see that this breast tissue here has a little bit of structure to it, that is the kind of thing that medics are looking for. That was actually a tumor. So we were able to actually image a cancer tumor with this technique. Maybe I think this is the last example of imaging that I have, just to show an example that is useful for biology. This is a preborn mouse. It's a mouse embryo. Mice embryo are used a lot in genetics because they're actually very good for experiments, it seems. A mouse has a litter which is quite large, like 6 or 7 children at once, and so it's good for statistics. And so you can, some of our colleagues, again, in the Mouse Institute at the MRC, close to Rutherford Lab, what they do is they want to see the effect of their phenotyping. They want to see the effect of different genes on mice. And so they change a gene within a mouse before impregnating it, within a litter before impregnating. And then they want to see how that effect, that gene, propagates into the litter of mice. And so then they do this almost every day. They change a different gene, they will produce a litter. They have to do 3D imaging of the mouse embryo. And each of these things normally would take a day on one of their machine. And so we also did X-ray imaging of these. And again, we did multiple projections so we could form 3D images. So here's the 3D images again. You can see the tomograph worked out quite nicely. These mice have been stained with iodine just to make it more strong. So it's mostly absorption spectroscopy in this case, but you can see that there are features that come out of this tomograph, like the skin and certain features within the material itself that are due to that are enhanced because of the phase contrast. Obviously, this is completely penetrating the X-ray radiation, so you can look at different features within the mouse. So again, they might be interested in how a gene will change the size of the liver or the size of the tongue or the eyes or whatever they're interested in. So being able to take many of these images in a very short duration, we could cut down what it takes them to do in days. Hopefully, in the next generation of lasers, we'll be able to do it in less than an hour, definitely less than an hour, maybe 10 minutes or something like that. And so that's another one of our near-term goals, is to actually just to be able to do these tomographs faster than we can do at the time. And that's purely dependent on laser technology at the moment. What I also would say is that not just can we move brighter by just having brighter lasers that operate more quickly, as we get to, people are now building these short pulse lasers at petawatt powers, 10 petawatt powers. These are laser systems that are being built right at the moment in Europe. And as you do that, actually you find the scalings is that not only do you get a brighter source, you also get a harder source. And so these sources, once you get above 100 kilovolts, yeah?
Sometimes your voice is not very clear. Can you check your mic?
I'm sorry, it's the best you're going to get. Sorry, okay. I'll try and be a little closer to the screen.
Yeah. Yes, sir. Yes, we are a little close to the mic.
All right. Okay. So anyway, these laser systems are in the process of being built, and if you get above 100 kilovolts, so 100 kilovolts is your standard medical X-ray machine, that is enough to penetrate a human body. So once we get to that kind of energy, then you can actually think of not just the samples that I had were obviously ex vivo, they were out of body samples. We can start thinking about doing in vivo imaging as well. So actually directly imaging human well, probably we're not going to do humans first of all, unless somebody wants to volunteer their wife. So assuming Röntgen is there, we will probably start with animals again, small animals. Okay, so I'm almost done. There was only one thing that I wanted to say finally, and that's just because like where we go. So I talked about some near-term goals, and the far-term goal is where can we push this technology? What limits that technology? And so obviously I told you that the modern, so what our source is already very comparable to third generation light sources, the synchrotron sources, of which there are many around the world. What we would like to do is to even make some of those fourth generation sources. You remember I talked about SLAC and DAISY, the big few kilometer long accelerators, and actually having some significance to making those kind of light sources, which are incredible. They're again orders. I mean, even if I show you, sorry, I try and go back. Let me go back. That's interesting. There you go. If I show you on that same plot, where the X-ray lasers are in terms of this parameter called brightness, you can see that they're already 10 orders of magnitude brighter. So you can actually image viruses like COVID before coherent diffraction imaging before you actually destroy it. So just one shot of something like this, an X-ray free electron laser, you can image a whole virus, and so obviously that's really powerful technique. So can we do something to be used in electron lasers as well? In fact, I think maybe some of the speakers later in the seminar series will talk about something like this as well. But we're considering it as well. Like, rather than using the radiation directly from our Wakefield accelerator, is to take that acceleration and pass it through a long undulator, so a much more defined undulation. If you remember the tune of my undulation within a betatron wavelength, you will have seen that the wavelength was changing all the time, the energy was changing all the time, which means that the X-ray radiation was changing all the time, that the wavelength was changing. And so there was no chance for a feedback mechanism. There was no chance to make a laser. However, if I take that electron beam and I make it high enough current and pass it through an undulator, there is the potential that I can, again, in a simulation, you can see this start of electron beam, where now I have a laser wave overlaid, and that actually causes this bunching within the electron bunch. And that bunching, actually, these bunches are now smaller than the emitted radiation wavelength. And because of that, all of the electrons within this bunch, rather than emitting radiation randomly in different phases, they actually produce radiation all in phase with each other. They are all coherent emitters. And because they're coherent emitters, they produce light which is in phase with what produced the bunching. And so this is a feedback loop that just gets brighter and brighter. So that's the principle of a free electron laser. Free electron laser, making a free electron laser is tough. Even already, if I've said we've made a compact accelerator which now goes from being hundreds of meters down to centimeter, at least for the plasma part, actually still the actual undulation bit and the feedback mechanism is difficult anyway. And so you will need at least typically hundreds of meters for the undulator section. So this is not an easy thing to do. You need a really big facility to be able to even consider this in the first place. And so people are talking about actually building plasma accelerators where there will be an undulator on the back end of them. It's a big project in Europe called Eupraxia, which will actually try and do that. But you can see that the scale of this is already huge anyway. It's going to be a very expensive thing. Then why would you even consider the plasma accelerator? Well, at least the plasma accelerator makes the acceleration part smaller. So at least you've kind of halved the complexity of the whole project. However, some of the things that you will need for a typical undulator, as I said, you need in the tens of GeV range. So people are making smaller undulators, and you could do it with a few GeV, maybe a couple of GeV. So LCLS is a 2 GeV machine now because they use a shorter duration undulator. But anyway, you need high energy electrons. That's an obvious thing to start with. As I said, the gain depends on current. The gain length you see here is current to the inverse third. So it's a very slow parameter, very slow change with current. So you need very high currents to make the gain very large. You need kiloamps, which is actually very difficult to do as well. You need small spot sizes. I mean, that actually is not so hard for our plasma accelerators to do. I said they are generally small in spot size, but two things which are really important is that you need an electron beam that's very, very good in quality. So you need something that's called an emittance. The emittance is actually how quickly that electron bunch spreads when you focus it. And again, that's a relative challenge for plasma accelerators, though people have ideas how to make the emittance of the plasma accelerator better, just so that the beam won't diverge and go out of the undulator, for example. And this probably is the hardest thing. This is remember I said you want the radiation produced by all of the electrons to be roughly the same frequency. Well, that means that all of the electrons should have the same wavelength. And you can imagine that the wavelength depends on the energy of the electrons. And so actually that makes a requirement on the energy spread of that electron bunch as well. The electron bunch energy spread should be very, very small. And for the moment, we at the best we can do with plasma accelerators is order of percent level. You probably want to be an order of magnitude below that to really make a good bright FEL with a laser wave field accelerator. So that's a very difficult thing. But anyway, all of these things are challenges, and obviously people are working towards all of these challenges for the next generation. So so that's it. And at the end of my talk, I just give you the conclusions again. So we do make plasma accelerators on the GeV scale. Again, we have some collaborations. I think you had Rajiv talking to you in one of these similar lectures before. We have collaborations with the TIFR, their new facility in Hyderabad, which will be a petawatt laser. We'll be able to do very similar things. And there are other actually facilities now being made in the world, which are just, they're not laser facilities anymore. They are going to be just Betatron facilities. They will have a beamline that actually can do some of this imaging all of the time. One particular example is at the Rutherford Lab in the UK. There's a new, very expensive laser, EPAC, being built, which Rajiv is actually in charge of building, actually. And one of its main goals will be Betatron imaging. So we can make very bright X-ray sources with those new lasers, as good as the generation sources. That those X-rays that we produce are perfect for ultra-fast imaging, imaging things on a fast time scale. Because of their small source size, they're perfect for high resolution imaging and also for doing phase contrast imaging as well, like these examples on the right-hand side. And their brightness flux can do things like tomography. For tomography, you need a lot of shots. Lasers are being developed which will produce a lot of shots and be able to do this kind of imaging in a fraction of the time that we are able to do it with standard X-ray sources now. So it's a pretty exciting field. It's a pretty exciting time as well in this field, and lots of things happening. And thank you for allowing me to tell you about it. So thank you. Another drink of water. If anybody's going to talk, Daphne? Silence. I've lost everybody. Hello? Hello? Did my screen just change as well? I don't know when that happened. So,
hello.
Hello.
Hello. Hello. Pawan is here. Your lecture, I think that has finished. Your lecture is over?
Yes, finished. Yeah.
Okay. Please wait.
Garima? Dr. Garima, you can take over because I think the voice was not clear. at the end, so we couldn't make out. Garima?
All right. Sorry about that.
There was some, the voice was very bad, especially at the end, during conclusions. There was so much of breakage of, too much of breaking of voice. So,
maybe it's this movie. It's
some network issues, maybe. Some network issues.
Yeah, maybe it's using too much bandwidth. Sorry about that.
No, it's okay, it's okay. Not in your hand and not in my hand too.
Do you want me to say the conclusions again? I could very quickly say them.
I think you can go through the conclusions again and then we'll...
So if I just say conclusions very, very quickly. So we do produce very bright sources of X-rays. And I think I said that there are a number of facilities being built around the world, which will actually be just dedicated towards this imaging. Including, for example, the EPAC facility at Rutherford Lab. And then some of the important properties of the imaging is that I showed that it's on a very fast time scale. So it's very good for ultra fast imaging. For example, at shock breakout imaging, I showed it's a very small source size, which allows you not just high resolution imaging, but it allows you to do these things, which is phase contrast imaging. And also, this thing was turning a second ago, because you need a lot of shots to be able to do this, to be able to do this 3D imaging. As we are developing lasers with very much higher rep rate, then we will reduce the time that we can do this kind of three-dimensional imaging to a fraction of what it takes now. And so these are some of the important goals for our field. So thank you.
Okay, so thank you so much. Garima, Dr. Garima?
I apologize for the...
Okay, in the meantime...
I can hear it. I don't know if there are questions. I don't know if you have people.
Are there any questions? People can raise hand or they can unmute themselves. We can take up the question answer session and people can raise hand for that or write the question in chat box.
This is Dr. Sandeep Kumar from Manav Rachna University. Zulfikar, it was a really nice talk. Actually, I have one question. When you talk about the radiation pulse characteristics obtained from this betatron source, so how do you compare it with this fourth generation X-ray free electron laser? Are they better in terms of brightness, pulse duration, emittance, or energy spread?
Oh yeah, yeah, definitely. They're all. I mean, we're nowhere in the league of the. I think I showed this. Can you see that?
Yes, yes. I mean,
so this is roughly where we are now. This is like a little bit of a cheat of. It's a parameter that tries to put in all of the features of an X-ray source all together. So it has the small source size, small divergence, small bandwidth, and small source duration. So because our source duration is very small, we can have numbers which are very high here. Anyway, our average flux is very comparable to, you can see these things. Petra 2 is an old generation synchrotron source, third generation source. However, we are if you look at the scale here, we are 10 orders of magnitude away from where the XFELs produce energy. And so, for example, the energy in one of our pulses is of the order of picojoules, maybe microjoules, whereas an XFEL will produce some tens, hundreds of millijoules of X-rays in a single pulse. So that's an amazing difference. And as I say, one example of how they use this is so normally it's almost impossible to do imaging of viruses because any kind of motion, it's such a complicated object that as you X-ray imaging it, any motion would blur out all of the features that you would have in the imaging of that. So what they do is that they actually do it in one pulse. They have so many photons that they can actually make an X-ray crystallography of a virus and actually produce a diffraction pattern all in that one shot. just because they have so many photons before the virus is actually destroyed. The virus is actually, because so many X-rays go through it and get absorbed, it'll actually blow itself up. But it doesn't matter. It's all happened in such a short time scale that they have the image of it, and they can reconstruct it already. So that's why I talked about right at the end why we are interested in not just having the beta-tron radiation that comes directly from the plasma accelerator, but actually taking the plasma accelerator beams and putting them into an undulator as well, so that we can make our sources brighter as well, and hopefully a little bit more compact too. But they'll then be as compact as this. This is not a thing that could fit in a hospital, whereas our sources maybe could fit in a hospital.
Okay. Thank you very much. Yeah.
Okay.
And actually, I have one more question. Do you pre-modulate the energy before entering to the undulator in Betatron source? Pre-energy modulation or density modulation of the electron beam?
So actually, all of our electron beams, the ones that I showed, I don't know if I can go back here. The ones that I showed are actually produced within the laser. Oops, sorry, went too far. These electron beams, they are actually produced within the plasma itself. So we didn't actually inject them externally from another source. You could do that, and you could, in that case, you could modulate them. There's two challenges of that. First of all, the source size of the accelerator is very, very small. Compared to a conventional accelerator, it, as I said, is tens of microns in that dimension, tens of microns in that dimension. So that's actually a very challenging experiment. And so people haven't really done that very well yet. The other thing is then if you want to pre-modulate on an X-ray FEL wavelength, that wavelength is even smaller still. And so you need another X-ray source to pre-modulate. You could think using like a harmonic source to do XUV pre-modulation, which they want FELs now, but to do it at X-ray wavelength seems very, very difficult. I don't see an easy, obvious way to do that.
Okay, sir. Okay, thank you very much.
It's a good question. Actually, it's a good idea. If anybody did come up with a way of doing it, then that would be a big advance.
Is there any other question?
Any other question? I think there was a question by Mr. Pankaj, Pharmacy. He had written in the chat box. Pankaj sir, you can ask your question directly.
Pankaj sir.
Question yeah. Sir, what are the unique properties of laser plasma accelerators based on the X-ray radiations?
I'm not sure if you can still see my screen. Can you still see my screen?
Yeah, might you have shown, sir?
You can still see my screen?
Yes, sir, we can see your screen.
Which screen you're seeing, I don't know, but let's see if I can.
It is showing acceleration.
Yeah, okay. I did try and no, it's not moving. Okay, it's stuck. So I did try and show some of the properties. So I guess the two most important ones are because the laser itself is on such a short time scale that you can start doing ultra fast imaging with it. And we haven't really explored that. I mean, we're trying to do things on the femtosecond time scale. I mean, even the examples I showed were on a nanosecond time scale, but we should be able to study things on a femtosecond time scale. So things like with absorption spectroscopy, some of my colleagues are looking at how population levels in solids fill up on a femtosecond time scale. So that's kind of interesting. And then the other important thing I already talked about is the very small spatial scale. And because of that very small spatial scale, like I said, not only do you get very good resolution, but you can do this phase contrast imaging. You can do phase contrast imaging in other ways as well. You can actually try and make phase contrast by using gratings and optics, X-ray optics. It's very much more complicated and very less efficient. Here, we're just using the fact that it's a very small source of radiation that we produce and let it propagate. Free space propagation is the easiest thing possible. All of those images that we did were the easiest thing you could possibly think of doing. So I think that's very powerful. If a technique is simple, I think that actually makes it even more powerful. That as long as you have that source, then anybody could do that imaging.
Hello. Hello.
Was that?
Yes, Pawan is here. Actually, what is the effect of the azimuthal magnetic field on the beta tone radiation or X-ray generation from the beta tone mechanism? And the brightness will be increased, or I think when you apply the azimuthal magnetic field on a X-ray generation from the plasma channel or the cavity. So what is the effect on the azimuthal magnetic field? I think nobody did include the azimuthal magnetic field.
So are you talking about the azimuthal field of the plasma wave itself?
Yeah, beta tone, yes. Self-generated azimuthal magnetic field.
So you mean the field of the wake field?
No. Suppose azimuthal magnetic field self-generated in the plasma channel or a cavity. What is the effect of that field on the beta tone radiation or X-ray radiation? I think that the brightness will be increased or decreased.
So that there is an azimuthal magnetic field, if you can see my cursor again, directly within this bubble itself. So if you look at this bubble, right, there is an electric field which I'm going to say points the other way. So it increases and decreases. And that electric field, that time varying electric field, has a displacement current. And so that there is a magnetic field actually produced by the wave field structure itself. So there is a small magnetic field associated with that. To be honest, the magnetic fields, and then I think you said you could actually try and generate a azimuthal magnetic field here. You could actually make a channel and produce a magnetic field for this to go into. The truth of the matter is that generally, if you compare the plasma frequency to the cyclotron frequency in all of those cases, the cyclotron frequency is very, very much smaller because the fields are much smaller. The magnetic fields are much smaller. So the effect is not strong. This is not a magnetic undulator. This is undulating because of the electric field. So the predominant action here is because of the focusing force. That, if you remember, there were forces on the electrons inwards, and because of the electric field, and so that's the main effect. Now there will be a second order effect. So that's the first order effect. The second order effects of the magnetic field will definitely change this interaction. Owen, I invite you to study that because I don't think anybody has actually studied that in too much detail. Or maybe you have and I actually don't know about it. You want to comment? I don't know.
Okay, thank you. I will try to do.
Oh, you tried to do it. So you haven't done it yet?
Yeah, surely. Professor Tripathi suggests to me that I will talk to you. What is the
it's a good idea, but it's not the prime. It's not going to be the primary effect, right? The electrons will mostly radiate, will mostly oscillate because of the electric fields.
Yeah. Okay, thank you.
Okay.
Any other question, please? If there is no more question, then we can hand over to Dr. Garima.
Thank you, sir. Just a small announcement. Feedback link for the webinar series will be shared on the last day for all the 3 days, and then the certificates will be issued. Now, I would request Professor Sanjeev Goel, coordinator of the webinar series, to please come in for the vote of thanks. Sanjeev, sir, please, over to you.
Thank you, Dr. Garima. Am I audible?
Yes, sir.
Okay. Thank you, Professor Zulfikar, sir, for enlightening all of us with the remarkable knowledge sharing on radiation sources from laser accelerators and applications. It has been a very informative and interactive session indeed. We hope that the faculty members, the students, and the participants from outside world, whosoever attended this lecture must have been benefited in many ways. We are very grateful to Najmudin sir for giving us his valuable time. We hope he will continue in future too to kindle our thought process. We are thankful to all the respected participants for their keen interest and involvement throughout the lecture. Our thanks are to whole organizing team, Professor Monica Sachdev, Principal Pharmacy, and Professor Poonam Kumar, HOD, ASH, as conveners, Dr. Sanjeev Goel and Mr. Abhinav Kumar Agarwal as coordinators, Dr. Vikas Kotoch and Mr. Pankaj Kumar as co-coordinators, Mr. Santosh Mishra for technical support, Dr. Garima Garg as anchor, Dr. Pavan Kumar for inviting the internationally renowned speakers to this webinar series, and all those with whose support the successful beginning of this international webinar series could take place today. Thanks to Mr. Pavan Pandey, Assistant Professor, CSE Department, for giving the coverage to this event in the press and media. Our heartfelt thanks are to RKGIT Vice Chairman Sri Akshat Goel sir, Director Dr. D.R. Somaseka sir, and other academic and administrative authorities for their consistent support always. Thanks to all once again. Thank you so much.
Thank you, Sanjeev sir. With this, we will wind up for today's session. Thank you, everyone. Thank you once again to Zulfikar sir for a wonderful session. Thank you, sir.
Dr. Garima, one moment.
Yes, ma'am.
Everybody should switch on the videos, all the team members and the department members who are present, and so that we can take a photograph. And Garima, do the needful.
Okay, ma'am.
All of you, please switch on your video.
Yes, ma'am, it's done from my side.
Thank you, Garima. Thank you, sir. Thank you, Zulfikar sir. Thank you so much. And I think we should close now.
Thank you.
Hope to
Bye,
see
everyone.
you again. Thank you.
Yeah. Have a nice lunch.
Okay,
Or at least
thank you.
have a nice lunch.
Thank you. Thank you.
Thank you,
I will try to do the calculations and I will send to you.
Okay.
Okay. Thank you.
Bye.
Bye bye.
Okay. Pankaj sir, I think we can close in 2-3 minutes because we are not sharing the feedback link today. So we need not continue for much time.
Okay, madam. No problem. Okay.
Thank you, sir, once again. We'll take leave. अमित सर मास्क क्यों लगा लिया आपने?
मैम एग्जाम सेल की वजह से काफी मेंबर पास हुए ना इसलिए औरों की प्रोटेक्शन के लिए।
ठीक है, थैंक यू गरिमा, हो गया सर। क्लोज करें, लेट्स टेक लीव।
मैडम क्लोज कर दूं?
क्लोज कर दीजिए सर, आज तो फीडबैक लिंक शेयर ही नहीं करा है।
ठीक है।
Pankaj sir, you can end the meeting. Yes.
Okay, madam. Thank you.